Okay, so got a new gear. Yeah, you don't see anything here, but it's right here. Yeah. It's much better, but trying to get used to this surface thing. Let's continue on the mapping from S-plane to Z-plane. Okay. Yeah. Okay. So in the previous lecture, we have talked about the mapping, and the kind of mapping we're looking for basically from Z-plane to the S-plane, and the Z mapping is e to the power of est. Try a little bit thicker. Okay, so if S equal to sigma plus j omega, right, and the Z equal to e to the power of sigma t, and then e to the power j omega t. Okay, yeah. So one of the particular case we're looking at is we know second order system very well in a continuous system, and the second order system in a continuous system is okay. It's this one, and the pose of the system, okay, is this, and we denote that as a sigma plus minus j omega d. Okay, yeah. So and then we have several basically specifications in related to the second order system, basically settling time, rise time, time constant stuff, right? Yeah. But overall, you should also know that is if I map this pole into the Z plane using this equation at here, right? Using the equation at here, so basically you use the same thing. You end up with the Z equal to r theta. Okay, yeah, equal to r theta here. So what's r then? If you use this pole at here to do the mapping, and your r, right, equal to e to the power sigma t, and theta equal to positive negative omega dt. So sigma is this, omega d is this, and then you can solve for zeta and omega n in terms of r and theta. Okay, so this is basically the equation between zeta, omega n, and r and theta. Okay, so that if you know what the zeta is, you know what the omega n is, and you know very well how the system will respond, right, in the continuous domain, then but you probably don't know what the zeta, omega n, but you probably have what you have is r and theta, so you can basically backtrack as to what the system actual response would be, right? So let's take a look at the example at it here. Okay, here's a continuous system, okay. And there's no control, probably just okay, just a feedback. So for this particular system, we can derive the transfer function of the system very easily, and that can be derived between y output and input, which is this. And for this system, your zeta is 0.5, your omega n is 1. Okay, so second order system. Here's your zeta, here's your omega n. Okay, so now what we want is, okay, I decided to discretize the system. Okay, so look at it, the discrete version. So we use a zero order hole to discretize it. Okay, so with this one here, we can derive basically what will be the, if we call this is y of s, that here still r of s, and this is a sample data system, and we are going to be able to derive, like the midterm, we can derive pulse transfer function, right, based on this system here. Okay? So the pulse transfer function for the system is y of z over r of z. Okay, so first step you do is you get your g of s and then turn it to g of z, right? Okay, and then the whole system is g of z over 1 plus g of z. Okay, so in the end you end up with this. Okay, suppose that we're sampling using t equal to 1 second. Okay, so here t equal to 1 second here. So by going through the procedure, you end up with this pulse transfer function. Okay, yeah, there. Okay, so then this particular case, your pulse is determined by this one here. Then if you set the denominator equal to 0, then you can find your pole, okay, which is this. Okay, you find your pose, which is this one here. So complex conjugate pose, and if you write it into the Euler format, so r absolute r angle theta. Okay, so the r turned out to be 795, and theta is 0.89. Okay, so there's positive negative here, reading. Okay, so that's your. Basically, this is a pole location based on a zero-order Hode equivalent discretization, right? And with the sampling time t equal to 1 seconds. Yeah. So what's the purpose here? The purpose here is we want actually to examine here. Now, if you forget about everything, if I just give you this, see, look, this is the pole location of a certain system, right? And this is r, this is theta. And then the question here is, okay, so I wanted to know what kind of a damping ratio or natural frequency does this pole, which is a discrete pole, right, correspond to? You see what I'm saying, right? So what do? We have these two equations here, right? So we can plug into this equation and calculate the damping ratio and the natural frequency. Okay? Yeah. So basically plugging the r and the theta into this equation, then based on these two poles here, right? Based on these two poles meaning assuming you don't know anything about the sampling time. You know what I'm saying? Just assuming you don't know this. Just assume you just given this one here. Okay? Yeah. Then you plug it in back here to the equation. You will get this one equal to 0.25, and this is omega n equal to 0.9191. Okay? So that's your zeta omega n corresponding to corresponds to this discrete pole. But of course you know where this is from, right? Where this is from? This is from a continuous system whose original zeta is this and omega n is this, based on the sampling time capital T equal to 1 seconds. Okay? So now if you look at this one here, what's original zeta? 0.5, right? What's the zeta corresponding to this discrete pole? It's actually 0.25. That makes sense? Yeah? So what does that mean? So that means, see, here's your original system. Zeta is a 0.5. If you are putting a step input, then you're supposed to get maybe something like this, right? Because this is zeta 0.5, so your overshoot probably 16%. Okay, yeah. However, with the sampling, right, and you're looking at a discrete system now, right? Let's say we're looking at a discrete response, because this is a z transfer function, right? Okay, and your corresponding zeta at here is a 0.25 now. So what would you expect the response for y of k here if you give a step input. Your response, sorry? It's what? Slower? Well, zeta is smaller now. Your overshoot should what? Your overshoot should be bigger now, right? Instead of 16%, and you probably end up with, I don't know, maybe 30%, right? Or 40%, okay? But the response here, it's not continuous. It's supposed to be a staired things, okay? Because it's a discrete, right? Yeah. So that's basically the idea here. Your sampling time, right? Your sampling time, actually, because of the discretization part, does, modify your original system response, okay? Characteristics. So you can actually imagine. So what if I reduce this sampling time from 1, let's say, to 0.5 to 0.1 or even 0.01, right? So, and that zeta supposed to be actually getting, closer to the original continuous system. Okay? Yeah.
Is that because of the extra integrator, like that it gets bigger? Because as the sample unfolds, holds it at a lower value for a little longer, the error is built up more, or is that just?
Yes. Actually, introducing this zero-order hold, right? You're introducing a phase, basically a phase delay into the system. Remember that zero-order hold? I was when we talk about the equivalence to numerical equivalency, right? And I mentioned that the zero-order hold introduce a half sampling time delay. Okay, right? So when you see introduce a delay, basically you're introducing a phase delay here. And in the control system, everything is about basically the phase. If the phase is there's too much phase delay, right, then the control system will become unstable. Yeah. Okay. Good. So you can try. I have a simulation code in the lecture notes. You can try it by changing different sampling time. Okay, and observe the response of the system. Okay. So now let's look at the mapping. Now keep looking on the mapping part. So what I wanted to do now is I want to look at the mapping of some special loci, okay, in the continuous domain. Okay, and then we'll look at how would that be mapped into the Z plane. Okay, yeah. So first we're looking at is that we're going to look at this case here. We're going to look at the mapping, okay, of the constant attenuation loci. Okay. So what's a constant attenuation loci? It's this. So that remember that S has a sigma plus j omega d, and the sigma is equal to negative omega n, right? The sigma is negative omega n. So if you look at the response in the continuous domain, right? If you look at, let's say, for example, if I look at the impulse response, okay, the impulse response, you can derive. You remember that formula. This is basically omega n for second order 1, zeta square e to the power sigma t, sine omega dt. Right? That's the impulse response. So if you plot it out, you have basically some kind of sinusoidal. At the same time, it's being sandwiched basically by that e to the power sigma t. Okay, so this sigma basically here, right? We can call that it's kind of attenuation, right? Sigma here, we can call that it's kind of attenuation there. So constant attenuation loci basically means in the S domain, I have a constant sigma. So maybe the sigma is at here, sigma 1, or maybe the sigma is at here, sigma 2. But along this line here, right, is a constant. Okay, that's what we call basically constant sigma. Okay, so a sigma we consider as an attenuation, right? So apparently, if you look at this one here, I mean, every pose on this one will not be stable, right? Because it's on the right side of S-plane, and this is good. But overall, right, as long as a constant pose along this straight line here, vertical line here, how would that be mapped into the, this is S-plane, how would that be mapped into the Z-plane, right? That's the whole idea. This is actually pretty simple. How do you do the mapping again? Your mapping is Z equal to e to the power of st, right? Yeah. And s here is this. So you have a e to the power of sigma t and then e to the power and then the rest of the term. So the current situation is sigma is a constant. If sigma is constant, then the absolute value of z is always this, right? It's always this. So basically means after the mapping, right, the pose for after mapping of all the points there, you know, into the z-plane, okay, the pose in the z-plane, the commonality is what? The magnitude is a constant. Okay, magnitude is constant. So if magnitude is constant, which means what? Which means basically it is being mapped into a circle, right? Into a circle, because this is basically r, right? This is r angle theta. So this is r here. Okay, yeah. So it's a circle. So for this one here, maybe the radius for this one here, right? It's e to the power sigma 1 t. Okay, power sigma 1 t. So if we wanted to be a little bit picky here now, if this is as e to the power sigma 1 t, where do you think the e to the power of sigma 2 t would be? Would that be within this one here, or would that be outside here? This one, for this line here, would it be within? This is another circle, right? Would the circle be within this one, or would that be outside this one? Outside, right? So it's not only just outside here, but it's actually outside another circle, which is a unit circle, right? A unit circle. Okay, yeah. So this circle here is e to the power of a sigma 2t, right? The radius. Okay. So basically, constant attenuation loci is mapped into a circle, right? In the z-plane. Okay. Yeah. Okay. So that's the first. First loci there. Okay. Second one. Okay. Let's look at the mapping. Okay. Of this so-called region of minimum settling time. Okay, TS. So settling time, we talk about the settling time basically when we learn reviewing the second order system. So we said if we're using 2% of the settling time, we can find the settling time between the settling time and the zeta and omega n is this much of a quantity, right? Yeah. So and that's basically 4 over negative sigma, right? Sigma is negative sigma equal to negative zeta omega n, so there's a negative here. Okay. Yeah. Now if we think it's a minimum settling time, basically we say generally we say, okay, I want my settling time to be less than, let's say, 2 seconds, right? So this is your minimum settling time. Okay, a minimum actually should say maximum settling time, isn't it? Because you don't want to be more than that 2 seconds, right? Yeah. But anyway, you know what I'm saying here. Maybe that should be maximum settling time. Yeah. But anyway, so if you translate this one into the graph, right? You can see essentially what does the sigma? Sigma essentially is a constant again, right? Sigma is a constant. So it's like this. So here's a sigma here, and your sigma maybe is just equal to what is that equal to? Let's say maybe just equal to 4 over a Ts negative, right? So sigma equal to 4 over Ts negative. Okay, is that good, right? Yeah. Now, if we wanted this is always maximum 2 seconds. So basically, your region for this for the sigma is on the left side, right, of this straight line here. Okay, of the straight line. Okay, and this straight line, as we just learned in the part 1, this is called continuous attenuation loci, and this vertical line is mapped into a circle, right? This line is mapped into a circle. Okay, this line is mapped in a circle here, and that circle radius is e to the power sigma t. Okay, and now what we want is we cannot pick a pole on the right side of this straight line. We can only pick a pole on the left side of this straight line. Then, which means in the z plane, right after the mapping, you can only pick a pole within this unit circle, but not unit circle, within this circle here. Does that make sense, right? Yeah.
And include the circle.
Yeah, and include this circle. Yeah, as long as you include this equal sign here, right? Yeah. Okay. So that's the idea of this second one here. So mapping of this constant, mapping of the region, right? So now it's not just a loci now. It's also a whole bunch of area in the S plane, right? Where is that going to be? Okay. So the third one, let's look at this one here. This is called mapping. Okay, of constant frequency loci. Okay. Constant frequency loci. So what is a constant frequency loci? Here is the S plane, okay, and this is j omega, and this is sigma axis. Okay, yeah. Constant frequency, it's basically comes from your S. The pole is equal to sigma plus j omega. Let's see, right? This is your poles here. Constant frequency basically means this omega is a constant. Okay, so the imaginary part of the pole is a constant. Imaginary part of the pole is constant, meaning you can draw a horizontal line, right? And every pole on the horizontal line has the same omega. So let's say this is omega 1. Okay, j omega 1. Let's see. Okay, and you can draw another one. Let's see here. This is probably j omega 2. Okay. Yeah. So how will this be mapped here? Now let's assume, okay, one thing is let's assume both omega 1 and omega 2 are below that j omega s over 2. Okay. So why do we make this assumption? Is because if you remember in the first lecture we have this so-called primary stripe, right? And and then beyond the primary stripe, and it'll basically be repetitively mapped to the same location. Okay, yeah. So stick to the same idea of the mapping. Z equal to e to the power of st. Okay, capital T. Okay, and how is that going to be now? Is it sigma t and then sigma j omega t, right? Sigma j omega t. Okay. So this is not a constant, so that could be changed, the sigma. But this omega is a constant. Omega is a constant, which means what? The theta is a constant, right? The theta is constant. So theta is omega t. Okay, theta is omega t. So then if I draw the mapping, okay, on the z plane. Okay. So here is the first one, j omega 1 s. Okay, j omega 1. Okay, j omega 1. then after the mapping, right? After the mapping, in the z plane, you can have a time varying value for the r, but the theta is always constant. So a complex number, what's complex? This is r, this is theta, right? This is theta. But now r, you can change it any way you want, but theta doesn't change. So what does that mean? That means it's going to be always a radial line, right? It's always a radial line. So let's see, maybe the first one here is this omega 1t. So this is basically your first mapping, right? This one here is mapped to here. Okay, it's mapped to here. Okay, so that's omega 1 mapped to this line here. So what do you think about omega 2? Where is that going to be? Would that be somewhere here, or it should be actually where? It should be here, right? So this one here is theta equal to omega 2t. Okay, theta omega 2t. What about this one here? What about the line passing through that j omega s over 2? J omega s over 2. Where do you think this one would be mapped into on the in the z plane? Horizontal, but where? Like this? No. This one here, right? So for this black one here, the theta equal to actually pi, right? After mapping over here, right? That's the j omega s over 2, the line being mapped here. Okay? Yeah. Is that good? Yeah. If you have a line underneath this guy here, let's say if you have a line underneath here, so let's say j omega 3. So omega 3 is a negative number, right? Yeah. And then you would be having is omega 3t, right? After the mapping. Okay? Yeah. And moreover, see, I draw the horizontal line passing through the both right and left plane, right? Okay? And we know that on the right side, on the left side, it's a stable one, but on the right side, it's an unstable, right? Okay. So anywhere the separating this one here or on the j omega axis, it's actually what? Is r equal to 1 unit circle, right? Unit circle here. Okay. Yeah. So basically, for the right side, for the left side, this portion is actually the portion within the circle, right? Yeah. Okay.
So any point along that line, your R,
yeah,
represents any point along the horizontal?
Yes. Yes. Yeah. Maybe you can think a little bit deeper here. For a point on the infinite left side, okay, let's say along this line here, on the infinite left side, where is that going to be mapped to? You know that point is going to be on this line here, right? Where? Dang.
I can't see your cursor.
Oh, you're right. Gee, I forgot that. I have a. Where did my yeah. There we go. Forgot my old trick. See this point here, right? Which is on the infinite left side.
Is that going to be using origin?
Yeah, it's going to be mapped to the origin here, right? As that point is moving until here, how does it go? It goes right, and then it goes outside. Right? Yeah. Okay? Yeah. Good. So non-nature, if you understand now, then okay. So let's look at look at an example here. Okay. So I'll give you a region. Okay. This is basically one of the kind of assignments you will see. So if you have a region over here, okay, and this is sigma equal to negative sigma 1, sigma equal to negative sigma 2, and this is j omega 1, and this is negative j omega 2. So assuming j omega 1 omega 2 a positive number, right? So we're using the negative right here. Okay. Alright, so how will this region be mapped into the z plane? Okay. So let's say this is a j omega s over 2, and basically we're assuming the region is inside the primary stripe. Okay, the primary stripe. Okay, so let's look at the mapping of this one here. All right, let's try the easy one maybe. There are two vertical lines, right? Those lines we call that with constant attenuation loci. Okay, and these two lines will be mapped into a circle, right, in the z plane. Okay. Sigma 1 apparently is less than sigma 2. So the circle for this one here should be, is a bigger circle or a smaller circle? Bigger. Okay, so that's the first circle. And this second circle is over here, right? Second circle. So you can label this one here, let's say r equal to e sigma 1t, and negative sigma 1t. And then you can label that one there as r equal to e to the negative sigma 2t. Okay? You can label it. And then your region is, yes, Remy?
Both inside the unit circle.
Yes. Yes, both are going to be inside the unit circle, right? Because they're all on the left side of the S-plane. And then your region is within the two vertical lines. So which means in the Z-plane, without considering the two horizontal ones, the region is actually what? It's between this, right? That's the donut part, okay? And then can now consider the two horizontal lines. We know the horizontal one constant frequency, and they will be mapped as a radial line, right, in the S-plane. And the first one is a positive, so I don't know how much it is, but let's just say maybe the first one is radial lines over here, right? And the angle from here to here is omega 1t. Okay? And this, the lower one is a negative omega here, right? Negative omega 2. So you may be having is this one here. So that's negative omega 2t. Okay? Yeah. Okay? So your by looking at only the two vertical one, it's this ring here. And then if I just look at the two horizontal one, it's actually from where? It's from this radial line to this radial line, right? Yeah.
So you're not assuming that it is symmetric in both the angles would be the same, right?
No, not necessary. You mean the omega 1 is the same as omega 2?
Yeah.
No. So let's say the omega s over 2 negative part is over here, but they're still within the primary stripe. Okay, yeah. So basically, the two angle here, right? They are not necessarily the same. Okay. Yeah. So apparently, overall, right, your region in the S plane at here, it will be mapped into where? Okay, over here. Okay. Yeah. Is that good? Yeah. Okay. Here's another thing here, which is I thought probably would be useful. Is this? Let me label you something here. Let's say if this is A, this is B. So this is a line AB. Okay, it's a line AB here. And this is a line. This is E, and this is F here. Okay, let's see. So what's the nature of AB and EF in the S plane? They're perpendicular, right? Yeah. Where's the AB being mapped to? Circle. Where's the EF is mapped to? Okay. What's the relationship between this radial line and the circle? Perpendicular. Right? Yeah, it's not a two straight line, but if you simply look at this location here, you can always what? You can always draw a tangent line at this location, and that radial line is perpendicular to this curve or to the tangent line, right? Multivariable calculus, you know, a lot of things over here, right? So that's actually a quite important property in terms of the so-called complex analysis. So this is called conformal mapping. Okay. So conformal mapping, this is a part of the knowledge called, this is in complex analysis here. I mean, we don't need to go into the details of this. We don't really have a course like this. So essentially, the conformal mapping meaning is preserve this relationship, geometrical relationship, okay, when you're doing the mapping from the S plane to the Z plane. You know what I'm saying? Yeah. If there are two curves has this much of geometry relationship, right, perpendicular or tangent, after the mapping, you know, it'll have the same relationship. Okay? Yeah. Okay, so now let's look at two more here, which is probably the most kind of difficult type of mapping now. We're at number 4, right? Yeah. So now let's look at the mapping, okay, of constant damping ratio low C. Okay, constant damping ratio low C. So what's the constant damping ratio low C? So we have to go back to our second order system and the poles of second order system. So poles of second order system is negative zeta omega n plus minus j omega n 1 minus zeta square, okay, and which is z sigma plus minus j omega d as we have denoted, right? If you recall from the previous lecture, I draw this diagram here. Okay, if this is where the pole is, okay, if this is where the pole is, if I draw a radial lines passing through that pole, okay, right, and then we can find a theta, okay, for this radial line here, right, and we can easily prove, okay, that this sine theta equal to what? To the zeta. Okay, to the zeta here. Okay, yeah. So basically means if I pick another pole, and this is in S plane. Okay, this is in S plane. If I pick another pole over here, So that means these two poles actually all has the same damping ratio, right? Damping ratio. So basically this radial line, right? This radial line in the S-plane here, okay? S-plane here, okay, for a second order system, okay? We consider that as so-called constant damping ratio low C, okay? Constant damping ratio low C. Okay, so now the question is, how will this line, okay, be mapped into the Z-plane? Okay, that's the question now, right? Yeah. Okay, so yeah, actually, when I got my master's degree and had an interview, so one of the questions the guy asked me is this. I didn't really answer the question right. Apparently, you know what happens, right? I didn't get a job and end up here. So actually end up doing a PhD, so then you end up here, right? The butterfly effect. We're doing the mapping, so we stick to that e to the power ts. Okay, yeah. And your sigma is this guy here. So if we plug in the sigma here, so what do we get? So I'll get rid of the negative one for the writing. Just use a plus maybe. Okay. Yeah. And this one here, right? This is basically after plugging, you end up this one here. So we'll do a little bit manipulation. Okay. We're not changing it, just to manipulate. Okay. Only manipulate it. Okay. So here's what happens here. So for this term here, okay, for this term, I'm gonna change that into this. Okay, omega d over omega s. That's the first term. If you don't trust me, you can do this. What's omega d? Omega d is this, right? Omega d is this. Omega s is 2 pi over the sampling time t, right? Yeah. So if you're plugging everything here, you'll end up back to this one here, okay? Yeah. And then second term here, we're not going to do too much like this, so we just change the t, okay, to basically 2 pi over omega s. Okay. So that's the manipulation that I was talking about here. Okay. So if I look at this based on the manipulated expression at here, okay, then for this one here, so what is the R here, right? The R for this mapping, after the mapping, the pole for the R is what? Basically e to the power the first term, right? E to the power is first term. Okay, so e to the power okay, that's your R. And theta is this. So theta, you can use angle Z or theta, doesn't matter. It's this one here. So 2 pi omega d over omega s. Okay. So I don't know what the curve looks like yet, right? You know, after the mapping, but I know that with this mathematical expression, after the mapping for in general, right? This is the two expressions for the R and the theta. Okay, for the R and theta. Now let's go back to this. This is the constant damping ratio low C. So zeta is a constant. Okay, zeta is constant, meaning this is constant. Okay, so let's say you give, oh, zeta is 0.5, 0.2, 0.6, like that. Okay, then you look at the R. If this is a constant, so the R is actually just what? A function of what? This, right? And the theta is a function of what? Same thing, isn't it, right? So basically now I can see now if I'm going to map this constant damping ratio low C, after the mapping, the R and the theta will be both a function of omega d over omega s. Okay, so R and theta they are function of, right? They are function of this. Okay? Is that good? Yeah. So, as a matter of fact, if I look at a little bit closely here, okay, omega s we can't change, right? That's maybe just the nature you started with, sampling time, okay? But what is omega d here? Omega d is this term here, right? Omega d is this. So in terms of omega d, if I let omega d increase, if omega d is going to increase, so the r will actually what? Decrease, right? And the theta, omega d is increase, so theta is actually going to increase. Okay? Yeah. So r will decrease and theta will increase. Okay? So this r and theta, you look at it, this is actually mathematically, it's a spiral. Okay? It's a spiral. It's more of a logarithm spiral. Okay? And if you plot it out, so we look at omega d over omega s ratio. R started to decrease, right, from big to small, and theta from small to big. Okay, so your mapping is more of a look like, okay, like this. Okay, it's a spiral. This. Okay, so if you draw a line, here is the current one. See that? That's the theta, right? That's the theta, and this is r, right? And if you keep drawing, my drawing is not that good, but you know, if you look at this one here, this is r, and then this is theta now, right? So apparently, theta r is decreasing, the theta is increasing, right? It's a spiral here, okay? Yeah. But we don't really need, you know, the whole picture of the spiral here, okay? We only actually need from here to here, okay? We only need this portion here, okay? You'll see the reason here, okay? We need the reason. So let's see if I give you an example here, okay? Let's say zeta equal to 0.3. Okay, let's say zeta is equal to 0.3. Okay, then I'm going to look at this one here. Let's say omega d over omega s equal to 0.25. Suppose that the ratio of omega d over omega s is 0.25. Okay, so then what does that implicate? What does it mean for the r, right? Which is which one? This one here, right? Which is this. You have a zeta, you have this ratio, you plug it in, you can calculate the r. Okay? So what's r now? You can calculate this is about 0.61. You can also calculate the angle, okay, which is 2 pi omega d over omega s. So plug in this one here, which is actually 90 degree, right? It's 90 degree here, okay? Yeah. If I keep another one here, same for the same damping ratio. If the ratio of this one here becomes 0.5, okay, 0.5 here, then similarly your r will be 0.3725, and your theta would be 180 degree now. Okay, yeah, 180 degree now. So this is basically what you're gonna see now in terms of the mapping. Okay, there we go. When omega d equal to 0.25, 90 degrees theta. When omega d equal to 0.5, what was that? Pi, right? 180 degree. And this portion here is, where is that? Here, okay? It's 0.61. Okay? Yeah. And this portion here is a 0.37. Okay, yeah. That make sense? Yeah. Okay, so this is actually the reason here. So you see, when the ratio omega d over omega s is 0.5, your theta is at 180 degree now, right? Theta is 180 degree. What's the theta? Theta is r theta, right? R theta here. Okay, yeah. So in the discrete domain, so this will be basically translated into cosine, theta k, basically. Okay, when you translate into this sequence of numbers from the pole to the discrete to sequence number. Theta from negative pi to pi, if you recall that, is actually the maximum frequency you can get in the discrete domain. Remember that? Because cosine, when you have a cosine k pi, how does that change? 1, -1, 1, -1, right? That's your highest frequency, basically, right? In the discrete one. So in this case, we only need, if I draw the constant damping ratio mapping, okay, I don't need to draw the rest of them. I'll just draw this portion here, okay? I'll just this portion. And then you have this is for 0 to pi, right? 0 to pi. You also have a negative pi to 0. So basically, you have a symmetric curve to this one at the bottom here. Okay. So apparently, you can see for this curve, right, from here to here, that corresponding to what? The zeta equal to 0. This is 0.25, right? 0.3. This is going to correspond to zeta 0.3, okay, which is this radial line. Is that good? So this radial line is mapped as a part of the spiral over here. Okay, yeah. Okay, if I draw the radial line over here, basically, for complex poles, it always appear as a pair, right? So the other one maybe is bottom here. So if you draw another one here, okay, this is symmetric to that. Then the bottom one here will be mapped to where? Okay, to this one. Okay, yeah. Okay. So naturally, what we do is we wanted to know. Okay, so I don't want just one, right? Maybe I wanted this a whole bunch of lines here. So if I want a whole bunch of lines, this is what you're gonna get. So you're gonna get this cluster of constant damping ratio after the mapping. Okay. Is that good? Look at the last one, zeta equal to 0, which is actually what? The circle. What circle? The unit circle, right? The unit circle. And where is the zeta equal to 0? If I look into the at the S plane, which line is zeta equal to 0? According to this one, zeta equal to 0 meaning theta equal to, this is theta. Zeta equal to 0, theta equal to 0. So which means which part of the line now? From starting from here, what do you draw? Right. It's the g omega axis, right? Yeah. So it makes perfect sense. If g omega axis is mapped into the circle here, okay? So you should have the other half basically just mirror it, okay? Yeah, for this one. Is that good? Yeah. Then.
So you use the circle, that means that the frequency down like this, right, where your damping ratio is higher than kind of equals that. So
yeah, when zeta equal to 0, basically it's what we call is you have, it is a critical location, right? If you look at the time response in time domain, sinusoidal, there's no decay, and it's basically a constant amplitude, right? It's always oscillating. But if zeta is a little bit, or a little bit on the other side, then it started to diverge, right? Yeah. But if you have a pose, let's say on the z plane here, you have a similar basically idea. If you look at this one here, you will see maybe an oscillation basically, just like the continuous one. You will see an oscillation basically going on, right? But there's no decay. Okay. If you're looking for this point here, guess what? It's probably just up and downs, right? Okay. But a much higher frequency than this one, right? Yeah. Okay. I'll show you a picture later. Okay. Yeah. Okay. So that's the mapping for this. So let's keep looking at one more mapping at here. Okay. So we'll be able to put a whole picture together. So last type, this is actually the last one. Last one is the mapping of constant, okay, natural frequency. Okay. Again, I'm talking about constant natural. So mapping of, so be careful, this is not a constant frequency, it's a constant natural frequency. Okay, constant natural frequency. The pose that we're dealing with is this, and natural frequency is this omega n. Okay, natural frequency is the omega n here. So what we're saying is we're trying to map a loci, okay, for second order system, that this omega n is a constant. Okay, not the zeta is a constant anymore, right? Yeah, the previous zeta is a constant. So one loci make a constant natural frequency. So you see, if I sigma square plus this omega d square, okay, if I do this and then take a square root, okay, so this square of this plus the square of this, okay, and then square root, and guess what? You end up with just the omega n, okay? You end up with omega n. So what's sigma square plus this omega d square square root? This quantity, what does this quantity represent? This quantity represents what? The magnitude, exactly, right? The magnitude of this pose in the S-plane. And we want it to be a constant, omega n, which is omega n, right? We want it to be constant. So which means if I draw the loci out, it's actually basically what? Another circle, right? In the S-plane. This is S-plane here. The radius of the circle is omega n. Okay? So constant natural frequency in the S-plane, it's a circle with a radius omega n. Right? Yeah. How will this circle going to be mapped into the Z-plane? Right? That's the question. Now, we don't want to go through the math anymore. We can use the concept I was just talking about, the conformal mapping. If I draw a radial line out of the center here, what does each one of the radial line represent? Constant theta, or constant what? Damping ratio, right? Constant damping ratio. What's the relationship between this red and the blue? They're what? Perpendicular, right? They're perpendicular. Then after the mapping, the red and the blue should maintain the same relationship. And we know what the red going to be look like after mapping. It's this. Then after the mapping, the blue one supposed to be, the mapped curve supposed to be what? Perpendicular to each one of this, right? So basically, if I'm saying, okay, so how can I draw this omega n here? Then maybe I'm going to draw is at this location. I'm going to draw a curve perpendicular to this, right? At this location, draw another part of curve perpendicular to this. So you connect all this one here, so you will have a curve perpendicular to each one of this constant damping ratio low C. And that curve, right, is the mapped one for this. Does that make sense? Yeah. So anyway, what you're gonna see is, right, you're gonna see that after the mapping, this is what's going to look like. Okay, so you have a whole bunch of lines that are here, right? You have a whole bunch of lines, and that's what's going to be. Yeah, would that be good? Yeah. So, but if I don't tell you anything, if I just see, let's see. If I just see, let's see this. If I see, okay, here's a point. Okay, here's a point on this circle here. Okay, here's a point on this circle. Where would be this point be mapped to? Okay, let's say this is A point. Okay, this is A. Where would that point A be mapped to in the Z plane? What's the coordinate of A? The radius circle is omega n, right? It's omega n. So A is on the g omega axis. So this is actually, A is at where? J omega n, right? A is at j omega n. Then after the mapping, it's going to be end up at j omega n capital T, right? The theta angle for the A. So what's theta? Theta is omega n T. If I gonna draw and find the theta, maybe this is omega n T theta. Was that right? Okay. And where is that radius? Radius is a second here. This is, my mind is not working properly now. A is A location is 0 plus j omega n, right? So where is that going to be mapped to now? It's going to be mapped to, yeah, it's going to be mapped to the, to where? Unit circle, because R is, the sigma is 0, because sigma is 0, theta is this omega, so it's going to be mapped to where? To here, right? This is the A going to be mapped to here. Okay? The corresponding angle for the B location is, this is theta. It's supposed to be omega nt. Okay? Supposed to be omega nt. If I think the other way around, okay, the other way around, here's a B. Okay? This is the B location. And I can find the theta angle corresponding to B location, right? If I ask is, what's the natural frequency for this B location if you think it back into the S plane? How would I find that? You know what I'm saying? So let's say this theta is I don't know, 30 degree or 60 degree, whatever, right? Okay, for this B location. But if other question is, what will be the natural frequency, okay, based on this B location? What does theta equal to according to the current calculation? Theta equal to omega nt, right? So if you know theta, then the natural frequency is supposed to be what? If you know theta, then the natural frequency at this location is supposed to be the theta over capital T, right? Yeah. But the problem is you probably don't know what the sampling time is. You know what I'm saying, right? Because if I just, the question is purely just give you a Z transfer function without telling you anything else, right? You can figure out the location in the poles. Maybe it's B. You can figure out the R. You can figure out the theta, right? But if the question didn't tell you the sampling time T, capital T, you actually won't be able to tell what's the original continuous system natural time omega n. That makes sense? Yeah. Okay? Yeah. So this is basically the whole idea of the next graph. What I'm trying to show you here is when we draw this one here, this is from a MATLAB command called zgrid here. We show that using a so-called normalized, okay, oops, why so small? There. We show that using a normalized version. Okay, show the normalized version. So you can if you look closely here, those are a bunch of natural frequency lines. Okay, as apparently you can see all the lines are perpendicular to those what? The constant damping ratio lines, right? Okay. Now MATLAB, this is generated using zgrid. Okay, if you don't need to give any command, just type in zgrid. It'll generate this graph here. Okay, it'll generate this graph. Now, if you look at the labeling of the graph here, this is 0.1 pi over t. What's 0.1 pi? That's a theta. Okay, that's a theta. See, it's a theta goes from 0 to pi, right? Going to 0.pi. pi. So what it's trying to tell you is, here's the natural frequency. For example, this is the natural frequency 0.7 pi over capital T, supposed to be. But that based on knowledge, you have to know the capital T. Okay? Maybe what's really labeled here is just a 0.8. Okay, the actual value is 0.8. So that if you know this 0.8 and you wanted to know what the natural frequency is, then you have to know what? The sampling time. Is that good? Yeah. Otherwise, you just take it as this is 0.8 to the theta. Okay? Yeah. So that's a z-grid. Now, let's look at an example here. Okay? Let's look at example. Okay. May not be able to finish this now. So we have a zeta 0.25. Okay, here's 0.25. Suppose that we wanted to design a control so that we want zeta equal to 0.5. Okay, so this is the desired. Okay, yeah. And settling time. Okay. And TS, so let's say 2% settling time is 2 seconds. Okay, so less than 2 seconds. Okay, less than 2 seconds. We have a sampling time 0.2 seconds. Okay, so that's it. So let's see. The question basically is, what will be a proper discrete domain poles to give us, okay, this kind of a behavior. Okay, yeah. So, given the Ts settling time, the relationship between Ts and Z omega n, right, is this for 2% settling time. We want that to be less than 2 seconds. We have the desired zeta, so plug in zeta 0.5 here. So that basically means your omega n needs to be what? Greater than how much? 2 over here, 1, 4. So your natural frequency needs to be greater than 4 reading per second, right? Given the current settling time requirement. Then your omega d, your the damped natural frequency is this one here. Okay, is this. So now I have a pretty good idea now. I can do the mapping. I use this mapping here, and we'll see that what's the discrete pole now, okay, given the sampling time and after the mapping. So okay, here's the formula. You plug it in, plug in omega d, plug in capital T, plug in zeta, plug in omega n. Okay, we end up with this guy here. .67 angle, 39.7 degree. Okay, so that's the after mapping in terms of 5158 plus minus. You get plus minus. It's always a conjugate, right? So it's plus minus. Okay, yeah. So that's the location of the mapped here. Okay, or the mapped one here. Okay, then if we do this drawing at it here, how do you get it out of here? Try these commands here, okay? Seriously, try this, and how do you draw this one here? So here's my drawing. Okay, so this is the location. Okay, this is the location of the mapped pole. Okay, this is location mapped pole here, and this is the zeta equal to 0.5, the constant damping ratio low C, right? And what's omega n in this case? Omega n we calculate as what? 4, right? Minimum is 4. And what is the capital T sampling time? Is 0.2. So the number right here, this is actually what? The theta equal to omega nt. This is theta, so that should be 0.8. See that? Okay? Yeah. So that's the explanation of those numbers here. All right? Those numbers. Because you see, if this is 0.8, right? If this is 0.8, so I ask you the same question. So what is the natural frequency of the regional continuous system if I know theta is 0.8? What do? You use the theta divided by sampling time, right? Which is 0.2. Okay? You get back to the 4, right? But of course, if you're only giving here, if you just look, this is the discrete one here. and without being told the sampling time, you can't get back to this original omega n, right? Okay. Okay, so a little bit forward here. If the question asked is this, if the question asked is, you want omega n to be greater than 4, and you want the zeta to be less than 0.5. Okay, so this is the question. I want my damping ratio to be less than 0.5. And I want the omega n to be greater than 4. Or in other words, I want my sampling time basically like this, to be less than 2 seconds. All right? So this is basically become a slightly different question is this. I want my zeta, okay, if this is zeta corresponding to 0.5, I want my zeta to be greater than 0.5. What does that mean? That means the pole in the S-plane should be where? Should be here or here? Should be within this two sandwich or outside this sandwich? If I want my zeta to be greater than 0.5. Here, right? And I want my sampling, I want my settling time. Settling time is this. I want the settling time to be less than 2 seconds. It's here, right? So you see, if the two conditions put together, you're actually looking at is where? Can you see that, right? Okay. So then, if we refer to the same thing in the z-plane, where will be this region? Okay, where will this region be mapped to in the z-plane? Here I only map 2 points, right, from that example. But now I want to map the whole region now. So first, maybe look at these 2 lines. The 2 constant damping ratio line. If the boundary is this, right? The boundary is this. You want your damping ratio to be less than 0.5. Then where should you be? Should you be outside this or within this heart? Within the heart, right? Because you see those damping ratio lines here? What's the trend? As it goes out, it's getting smaller, right? Getting smaller. So you should focus on this inside here. At the same time, you want the sampling, you want the damping, constant. You want the settling time to be there. The settling time to be there actually means, as we derive, means omega n to be greater than 4. So what is omega n equal to 4? This is omega n equal to 4, right? You want your omega n to be greater than 4. And if I look at this curve here, this is one omega n, another. Guess what? So what's the trend for increasing omega n? Is it this way or the other way? As you look at this one here, you compare this curve and that curve, which has a higher natural frequency? This guy, right? This is higher theta, right? Higher theta over t. So then back over here, this is the minimum omega n. Then you want your curve to be on what? On the left side of that curve, right? Yeah. So put the 2 conditions together. Okay. You cut the heart by a piece. Okay. The rest of it is the region that will satisfy the requirement. Was that good? So just to maybe quickly summarize here, you can take a look at this diagram, okay, in the lecture notes. This kind of summarizes to, at each one of the location, what kind of a system impulse response will look like, right? Yeah. But anyhow, I think the point at here is one of the assignments you should do is, which probably I will retest you in the final exam. Given a region, in the S-plane, what's going to be in the Z-plane? and by making use of all the specialized losses. Okay, yeah.